Every year across the United States, more than 300 major power outages ripple through interconnected grids, triggering blackouts, economic loss, and in some cases, nationwide emergencies. Yet the work of inspecting energized high-voltage lines never stops. Linemen operate under voltages that would be instantly fatal, employing precision, conductive suits, and physics that most people have never heard of. Why can't these lines simply be switched off, and how do crews survive the invisible dangers lurking in every inspection? The answer reveals just how much modern life depends on razor-thin margins between safety and catastrophe. Across North America, the modern power grid operates as a single, sprawling machine. Every second, thousands of miles of high-voltage lines shuttle electricity between distant generators in cities, balancing supply and demand in real time. These transmission corridors are not isolated, they are interlocked, forming a web where the failure of one part can ripple outward and overload others. A single high-voltage line carries as much as 500,000 volts. Taking it offline, even briefly, forces that load onto parallel lines. If those lines are already near capacity, the overload trips protective relays, which then shut down more sections to prevent equipment damage. This chain reaction, known as cascading failure, can plunge entire regions into darkness within minutes. Grid operators track these risks constantly. During summer heat waves, when air conditioners push the system to its limits, there is little margin for error. Shutting down a major line for inspection or repair is rarely an option. The United States experiences more than 300 major outages every year, many triggered by a single weak link. In 2003, a sagging line in Ohio set off a blackout that left 50 million people without power across 8 states and parts of Canada. Utilities learned that even routine maintenance could threaten the grid's delicate balance if not managed with extreme caution. This is why live line work exists. Crews must inspect, maintain, and repair energized lines without interrupting service. The stakes are measured not just in lost revenue, but in the stability of entire cities, hospitals, and industries. Every decision in the control room and every action in the field is shaped by the knowledge that the grid's continuity depends on keeping these high-voltage arteries flowing, no matter the risks. Electricity at transmission voltages is governed by physical laws that leave little room for error. Michael Faraday's experiments in 1836 revealed that a closed conductive shell shields its interior from external electric fields. When a worker approaches a conductor charged with hundreds of thousands of volts, the difference in electrical potential becomes dangerous long before contact. Air under normal conditions can withstand about 30 kilovolts per centimeter. Exceed that threshold and the air breaks down. It forms an arc, a sudden violent flow of current through ionized gas. This is why even a hand extended too close can trigger a flashover. Routine maintenance on de-energized lines is fundamentally different. The circuit is isolated, grounded, and rendered harmless. Crews can climb towers and handle hardware directly, relying on mechanical safety rather than electrical protection. With live line work, every action is shaped by the need to control the electric field. Insulated tools, often fiberglass hot sticks, allow workers to maintain distance, while conductive suits and bonding leads bring the body and equipment to the same voltage as the line. Bonding is critical. By equalizing potential, linemen prevent current from flowing through their bodies, much like a bird perched on a wire. In this way, the Faraday cage principle becomes a practical safety strategy. Modern inspection technologies, including ultraviolet cameras, detect the faint blue glow of corona discharge, evidence that insulation is breaking down and air is starting to conduct. These early warnings signal when a component is approaching its limits. In the field, linemen rely on a blend of physics, engineering, and strict procedure to manage forces that are invisible but ever present. The next step is understanding how these principles translate into the specialized tools and protective equipment that make live line work possible. A live line operation begins long before a helicopter ever leaves the ground. Every step is scripted and rehearsed. The crew meets to review the line's maintenance history, recent inspection reports, and any known hazards along the route. Weather conditions, wind speed, and airspace restrictions are checked against strict go or no-go criteria. Each tool is tested for insulation and cleanliness, and the lineman's conductive suit and bonding leads are inspected for wear. Once cleared for flight, the helicopter lifts off and traces the transmission corridor, its pilot and lineman communicating constantly by radio. As the aircraft hovers near the energized conductor, sometimes less than a dozen feet away, the lineman extends a fiberglass wand tipped with a conductive hook. A blue-white arc leaps from the line, briefly illuminating the gap as the potential difference equalizes. This arc, though controlled, is a vivid reminder of the forces at play. The lineman waits for the arc to settle, then attaches a bonding clamp, connecting the suit and helicopter directly to the line. Now, the lineman, tools, and aircraft all share the same voltage, eliminating the risk of current passing through the body. With the bonds secure, the lineman inspects hardware, checks for hot spots, and tests connections. Every movement is deliberate. When the work is complete, the process reverses. Clamps are released in order, the wand is used to safely break contact, and the helicopter withdraws. The entire sequence depends on absolute coordination. Any missed step, any lapse in timing, can turn routine maintenance into a life-threatening emergency. Protective equipment for live line work is engineered to manage forces that are invisible but lethal. The conductive suit, often made from a blend of Nomex and interwoven stainless steel fibers, turns the worker into a living Faraday cage. Every seam, glove, and boot must maintain electrical continuity, so the suit channels current around the body rather than through it. These suits are tailored for each lineman and inspected for broken threads or worn patches before every use. Even a pinhole in the fabric can compromise protection at voltages above 230,000 volts. Insulated tools, such as fiberglass hot sticks, provide another layer of defense. Each stick is rated for specific voltage classes and must pass routine dielectric testing, typically every 6 months, to confirm that the insulation has not degraded. Any trace of moisture, dirt, or hairline cracks can turn a tool from a barrier into a hazard. Bucket liners and aerial platforms use conductive grids bonded to the line, creating an equipotential zone that eliminates stray voltage paths. These grids, clamps, and bonding leads are checked for corrosion and proper function before every operation. Safety engineers stress that no shortcut is tolerated. A failed inspection means the tool is sidelined, regardless of schedule pressure. The entire system of personal protection depends on rigorous maintenance and absolute trust in every component. Wind, rain, and airborne dust do more than make a lineman's job uncomfortable. They can turn routine maintenance into a high-risk operation. Even a thin film of moisture on an insulator can lower its resistance, making it easier for electricity to arc across the surface. Dust or salt deposits left by wind or fog build up over time, creating invisible paths for current to escape. When a storm moves in, gusts can push conductors closer together or cause them to sway, narrowing the safe distance that keeps voltages contained. Crews often remark that on a humid morning, the air feels heavier, not just from the weather, but from the knowledge that a flashover could happen with the smallest misstep. Fatigue is another silent hazard. Long hours aloft, constant concentration, and the physical strain of working in full protective gear all wear down a lineman's focus. Most incidents do not come from dramatic failures, but from small lapses, a tired hand slipping, a contaminated tool, or a gust of wind at the wrong moment. In these conditions, the engineered safety margins that protect workers can erode without warning. Safety margins can shrink gradually, and human factors can turn a routine task into a serious incident. Every live line operation is built on layers of redundancy and a culture of relentless training. Before a lineman is cleared for work at extreme voltage, months of classroom instruction and field simulation are mandatory. Utilities require certification in specialized techniques, bare hand, hot stick, helicopter entry, each with its own renewal cycle and practical exam. Every procedure is codified in checklists, from pre-job briefings to post-job tool audits. Dielectric testing of insulated tools, for example, is scheduled every 6 months, with any tool failing even a single test immediately removed from service. Conductive suits are checked for continuity before every use, and bonding leads are inspected for corrosion or wear. Safety protocols demand that no step is skipped, regardless of schedule pressure. Safety engineers stress that strict adherence to protocol is the only defense against the unpredictable. Despite these safeguards, the fatality rate for linemen remains more than 7 times the national average. In this work, the system is unforgiving. Every safeguard exists because someone paid the price for its absence. Every hour, the nation's grid depends on work done inches from disaster. As our demand for uninterrupted power grows, so do the stakes for those who maintain it. Safety margins are measured in millimeters, and their vigilance determines how long the lights stay on. Thanks for watching.